All right, so this is our concept review for the energy unit. So we're also going to talk about work. So recall that we studied three types of mechanical energy in this unit. So kinetic energy, spring potential energy, and gravitational potential energy. Both of these are types of potential energy. And just to recall what some of these things mean, here for kinetic energy, this is the mass of the object, this is the speed. And for spring potential energy, this K is the spring constant of the spring, and X is the displacement of the spring from its equilibrium position. And here, this is the mass of an object. This is the gravitational acceleration or gravitational field. So on Earth, this would be 9.81 meters per second squared. And this is the vertical displacement of the object from some arbitrary starting point. Now, we often applied energy conservation to use these quantities. So recall that if you're in a closed system, so there are no external forces, energy is always going to be conserved. And if we assume that there's no loss of mechanical energy, so there's no energy turning into heat, there's no friction, that means we can use this, that the mechanical energy of a system at some time is equal to the mechanical energy of a system at some later time. In real life, this will never really work. In real life, you will always have some loss of mechanical energy because some of the system's energy will always get lost as a result of friction from thermal energy or air drag, right? Some of the, like if you drop an object and that object falls towards the Earth object system will lose some mechanical energy because the air molecules will experience forces from that falling object, and the air molecules will gain some energy, and the Earth object system would lose mechanical energy. Work. So in order to calculate work, you can use force and displacement of an object. So the work on an object is equal to the net force on that object, but only the parallel component of the force, right? And by parallel, I mean the component of force that is in the same direction as the object's displacement. And you take that and you multiply it by the displacement of the object, right? And that gives you the work that's done on the object. And technically, I shouldn't have vector signs here because my equation is really just about magnitudes here, right? This is the magnitude of force that's parallel to the object's displacement. This is the object's displacement. Now, a bit about signs. Work is going to be positive if the force is acting in the direction that the object is going. It's going to be negative if the object is opposite, or if the force is opposite the direction the object is moving. And these are vectors, right? This delta x, because what we really care about is the direction of these displacements. And also note that work isn't a vector. So even if it can be positive, it can be negative, that doesn't mean that it has a direction associated with it. Maybe think about it this way. If a force is putting energy into an object, work is positive. And if a force is taking energy away from it, work would be negative. You can also use areas of graphs to get work. So for example, if you have a force versus position graph, and you get the area underneath it, that will give you work. So if we have a force versus position graph for some traveling object, so this object is moving in the x direction, and the force is increasing on it. That's just this example. If we pick sort of two positions, x1 and x2, get the area under the graph between those positions, that would actually give us the total work that's done on the object by this force between those two positions. Okay, work energy theorem. This is the reason that work is really an important thing. It's because the work done on a system gives us the change in energy of that system. And this simplifies a little bit if our system consists of a single object. Because remember, single objects can only have kinetic energy. So if you think of a single object, the work done on that object is equal to the change in kinetic energy of that object. And sometimes this thing is called the work energy principle, whatever. It's sometimes called this, sometimes called principle, whatever. Okay, so the reason that this is useful is because it really lets us think about work as a flow of energy. Right, when positive work is done in an object, energy flows in. If negative work is done in an object, energy flows out. And the same is true for systems consisting of more than a single object, right? If the work on that system is positive, then some energy went into that system. And that might have gone in and turned into kinetic energy of something in the system, or it might have gone into potential energy within that system. But if work on the system is positive, energy went in. If work on the system is negative, energy came out. I think that's about it for energy.